So I'm going to tell you, I mainly wanted to talk about, so I really wanted to talk about mainly how to make use of SCION and all the neat research problems and research questions that come out of the architecture, but also ways, which is quite surprising, which is that you can actually deploy a next generation internet architecture in today's environment in a much easier way than we ever anticipated. So before starting and having this ambition of SCION enabling 1 million hosts in the world, and why 1 million and how we plan to do this, I'm going to briefly also give an introduction of how SCION works. And I also wanted to point out that this is collaboration with many different people around the world, but foremost also David Hauser, who's a professor at Magdeburg, and who's been leading the actual deployment of the university and research and education network, who has been rolling this out and dealing with all the challenges in rolling out the real architecture on the real networks. Right, so with that, let me get started, and I'll be telling you very briefly how SCION works, and so you have the background. But I didn't want to go into too many details, so I have one slide and then a few additional slides I'll quickly go through. So in essence, SCION is an inter-domain routing architecture, so it's like BGP, and so it's not competing with OSPF or any intra-domain architecture or SDN. It's really enables global connectivity. And what you see here on this diagram are different what's called isolation domains, or you can imagine also fault isolation domain. They don't isolate traffic, but they isolate faults. And they enable a grouping of different autonomous systems. So the small circles you see are different autonomous systems like KAUST or ETH, or an ISP like Swisscom or AT&T would be one of these small circles. And you see there's some structure. I won't go into all the details here, but in essence, these autonomous systems are in one of these isolation domains. And what SCION is doing, essentially, it finds path segments within this network topology. So it finds path segments between what's called core ASs. So these are the ASs providing global connectivity. They're the ones shown inside the gray ellipsoids. So they have a special role. But in essence, path segments are found inside isolation domains and how to connect different isolation domains. And then these path segments are being redistributed in the network, and when the host wants to communicate, and in this example here we have a host in F who wants to send traffic to a host in S, in autonomous system S. This host will fetch path segments from the network. So it asks the network infrastructure and says, look, I'd like to communicate with S. Which path segments could I use? And the network provides, in this example, these 6 path segments that can be combined in 2 different ways to achieve 2 different paths. And so this information then, also there's many layers of security. I should have mentioned this, as SCION is really a security architecture. So there's layers of security to protect the generation and redistribution of these path segments, but then also the information that goes into the packet. So when the host selects the path, it adds this information to the packet header, as you can see here. And there's also cryptographic protections using very efficient message authentication codes that are very fast to compute to protect also this information in the packet header, and the packet then follows this path to the destination. So you see, it's in a way a very simple architecture. And the good news is there's a lot of very nice properties that come out of this simplicity. So the first aspect is that routers don't need any more forwarding tables. So a lot of the issues with inconsistencies in forwarding tables or convergence processes to update these forwarding tables, all these issues are resolved because the information is in the packet header. And so routers actually become even simpler and stateless for the most part. Right, so this is the basic architecture. So essentially, the end host can select if it sends a packet on this lower path or on the upper path, and it can, for every packet, make this decision. And if a path fails, it can immediately switch to another path that's operational. So with this, I'll go into a little bit more detail. And the first concept I wanted to talk about was this notion of this isolation domains. And again, it's not isolating the traffic, so it's not for censorship, but it's really isolating faults. And you could also think of these domains as governance domains. So each isolation domain defines what's referred to as a trust root configuration, a TRC, which are all the cryptographic public keys that need to be relied upon for communication. So this is something that is locally chosen in the ISD, and so sovereignty of operation can be achieved because there are no external TRCs that need to be trusted for internal communication. Right? So you only need to trust this, the TRC of ISDs that you traverse. And so there is a notion, a strong notion of sovereignty that is achieved this way through this local selection of these trust roots. Also, what happens is if you look at scalability, and I'll show some scalability results later, splitting up the network into these domains also greatly enhances scalability of the routing system itself and achieves much faster distribution of and establishment of networking paths. So briefly, here's how it works. I'll very quickly go through these slides because I just added these slides last minute to also show a bit more technical background. So in essence, these the ASs in this gray part, the core ASs they're called, they issue routing updates, which we're referring to as routing beacons or path construction beacons, and they essentially trace paths through the network. And so only core ASs initiate these beacons, and all the other autonomous systems in the ISD then obtain different network paths.
Quick question, but when you say downstream, it looks like you're already assuming that the thing is organized in kind of a DAG.
Right.
But why? But if this is starting, how is it organized?
Right. So the internet has exactly this. Is already built in this way, right? So you have larger ISPs that provide the global connectivity. You have smaller ISPs with local connectivity, and this structure also mirrors that observation. And so if you're an autonomous system, eventually you will receive these PCBs, path segment construction beacons, and once you get one of these beacons, you can already communicate along the path along the path segment that this beacon has explored. In the next step, there's a path server infrastructure. So each autonomous system will need one of these path servers. You can imagine these being similar to DNS servers, but they essentially store path information. So locally, this local path server stores the path segments to reach the core ASs. So in this example here, all the 4 paths are being selected and are being registered at the local path server. And so at this point, already the local hosts can query the path server and get these path segments and already communicate with core ASs. So already within the ISD, communication is almost possible at this point already. But you see an interesting aspect is that the architecture enables selection of these path segments. So the local administrator can define which paths should be sent to and should be made available to the local hosts. And the same thing happens then for paths that are made available globally. So one can do ingress path control by looking again at these path segments. And in this example here, one of the paths is deemed maybe as a private path or maybe as a less optimal path. And so this path is deleted and not being made available globally, but the other 3 are. And then they're registered at a core path server, which is then enables the global redistribution of these path segments. So if another entity wants to communicate with S, they look up this information at this core path server and can then fetch these path segments that this destination has registered. You see the routing information is pool-based, so it's not redisseminated globally. It's really fetched if when needed through this path server infrastructure. So now here's an example of communicating within the ISD. So we have a host in R communicated with a host in S. So it fetched, in this example here, these green, what we call down path segments that S has registered. Then it fetched the local path segments that were registered. These are shown in blue. And then the core path segments in orange. And many different path combinations are feasible here. So one example is a shortcut path where you go up one step and then back down. So you don't always have to go through the core. Or you can also use peering links. This is very similar to how peering links work in today's internet. And also several other options. So we've actually seen in today's SCION network that is operational already a huge number of different paths that are feasible through different types of combinations that can be accomplished. So this also works at the global scale. So in this example here, we have these two up segments and then these 4 core segments and these 4 down segments. And so you can also, again, recombine them in a way to provide end-to-end connectivity. The way this looks like, just briefly, is you see the information of these path segment construction beacons or these routing updates that are being redistributed, and they contain hop fields, which then encode the actual forwarding decision in a more compact manner, also with a more efficient cryptography. And so there's digital signatures that protect the construction and enable verification of these PCBs. But then these hop fields and information fields are then extracted and recombined to then enable efficient forwarding, and that's what goes into the packet header. Each hop field is 12 bytes, so it's not short, but also not too long to have acceptable overhead for the end-to-end communication. So we say it's roughly 80 bytes additional overhead over IP, which is, of course, if the path is shorter, it's less. If it's longer, it's more. But that's roughly what we say, that it's roughly about 80 bytes additional overhead per packet. So surprisingly, this whole architecture has also a lot of scalability advantages despite the security. And here we looked at specifically at the beaconing system itself. So this routing update, and we compared it to BGP. And here you see the core beaconing. And I should say the beaconing inside an ISD is extremely efficient because only the core ESs initiate these beacons. So the overhead is almost negligible within the ISD. So these numbers I don't show. What's more effort is the beaconing between all the different core ESs, because each core ES is sending out these updates. And so a lot of paths are being created in the core, but nevertheless, the actual overhead is still extremely low. So what we see here is a realistic internet topology, and we compared the effort of SCION with the actual BGP information measured in today's internet. So we took exactly the same internet topology, and we had the ground truth of how much effort BGP is performing. So we looked at update size in this example here. And so we then looked at the different autonomous systems for which we had this routing information. And we can see that in the worst case, SCION used 15% of the overhead of what BGP performed. So on average, about 10%. So on average, SCION only needed to do 10% the amount of work of BGP. But actually, BGP only found one path. But in these examples, actually, SCION found 60 paths. So we stopped it after 60 paths. So it only uses 10% of the effort to find 60 times more information. When you compare this with BGP-SEC, it looks even more extreme. So BGP-SEC is not deployed, so we had to simulate this, and these are these red bars, and again normalized with respect to BGP. So on average, BGP-SEC has about 5 times the overhead of BGP, and you see SCION in blue at the bottom looks almost negligible in comparison. So you see the actual scalability of the system is extremely high because there's no convergence process, right? These path beacons go out, and these paths can be immediately used. There's no information in the routers that needs to be updated, or you have to wait until it converges. So there's a lot of pieces to SCION, which is shown here. So the idea was to achieve security against a lot of different attacks. So many different systems have been built over the last 14 years to provide different defense mechanisms. So for instance, a secure time synchronization system, or also a secure TLS, public key infrastructure, and so on and so forth. So many different pieces I won't be able to have time to talk about today, but the point is there's, for an attack and to defend against a given attack, to achieve certain security properties, you can then recombine these methods, these mechanisms, and to protect your system. So the point is a lot of opportunities to design a secure systems. So now there's a lot of benefits using this architecture, of course, foremost security and also protection to defend against denial of service attacks. But also path stability is very helpful when you have actual stable inter-domain paths. You know they don't change. A link may fail, but you can then select a different path. But unless the link fails or the path expires, you should be able to continuously use that path, which helps also network measurements and so on and so forth to achieve a level of transparency, what is happening in the network with my packets. Also control. There's a lot more control by the end host. We just had a discussion yesterday about the end-to-end argument. And so the point is actually SCION is even more end-to-end than today's internet, because the actual end host knows best about what type of paths the application needs. If the application needs low latency or a high bandwidth path or low jitter path, there's actually a lot of control by the end host. And this also enables a property called geofencing, where the sender can ensure traffic doesn't leave a certain jurisdiction. So it turns out in Switzerland, this is being used by medical entities because they have a compliance requirement that traffic doesn't leave Switzerland. And Switzerland is a small country, so a lot of traffic sometimes goes through Germany, say through Frankfurt, and in some cases traffic from, say, Zurich to Geneva goes through London, and so on and so forth in today's internet, which would then violate this compliance. And with SCION, you can then achieve a property, this geofencing property, and really say this traffic doesn't leave these boundaries. And finally, also performance can improve because of the ability to optimize for different properties, but also the ability to use several paths simultaneously can, in some cases, also provide higher performance. Right? So when you hear about this, you say, well, this all sounds great, right? You have high security, good performance. Why don't we all have this yet? And the reason is there's many challenges in this space. When you work on your internet architectures and you go visit an ISP, an internet service provider, and you say, look, I have this great architecture. Why don't you deploy this in your network? The ISP is going to say, well, what business can I open, and who are the customers that would want to use this? So who are the institutions that actually would purchase this? So you say, okay, let me go find some institutions for you. So you go talk to several institutions, and you say, look, I have this new internet architecture, and the institutions say, well, which ISPs actually provide this? So if it's only one, also they're not too interested in buying this because they may get a lock-in and the ISP may raise the price and so on. So it's very difficult to actually get started. So there's a mutual dependence here between ISPs and institutions deploying or entities deploying because they neither of them wants to get started with a new technology. There are also additional dependencies, additional circular dependencies like network hardware support. So when you go to hardware vendors and you say, please implement this, they obviously say, well, where is it being used? And similarly, when you talk to ISPs, they also say, well, which network vendors actually implement this? Because unless the big hardware suppliers implement this, why should a ISP actually deploy this? And similarly, dependence on standardization, dependence on operating system support, which depends on application support in a mutual way, and also user demand. So you see, it seems almost infeasible to get started with a new internet architecture. So what we did in the beginning is, sorry, we said, well, let's establish a virtual infrastructure, so an overlay infrastructure. We called this SCION Lab, which grew to quite a few autonomous systems, as you can see on this map. That is essentially using today's internet as an underlay. So it uses IP packets, standard IP packets. So SCION packets would be re-encapsulated into IP, sent across the regular internet, and received by the next entity that then would look at the SCION header, and so on and so forth. So this was established, and it grew quite nicely. And it's quite a nice network, and you can try out SCION using the SCION Lab by downloading a virtual machine image, and within a few minutes you can actually be on the SCION Lab network and start sending SCION traffic. But of course, since it's an overlay, you're inheriting all the vulnerabilities of the underlying network. Right? So from a security perspective, this is not that interesting, but from a testing perspective, you can quite readily make use of this infrastructure to connect and try it out. So this was good to get started, but then it was still difficult to convince ISPs and domains to actually make use of SCION. So what then happened was there was a use case that crystallized, and that the use case essentially was communication within a group of entities. Because what you need to do today, let's say you have critical infrastructures or data centers and different entities need to intercommunicate. If you buy leased lines between all these places, you're going to spend a lot of money buying these leased lines. And it's also takes a lot of work to establish these lines, and especially if you have a lot of home office users or several data centers, several offices and so on, you then end up having a lot of leased lines to purchase. Essentially, the number, if you want one-to-one pairwise connections, that number of connections grows with the square of the number of participants, right? So it rapidly becomes too expensive and too challenging. What's interesting is that SCION essentially provides the ideal case between leased lines and public internet, because it is a public internet infrastructure. One can purchase a SCION connection into this infrastructure and then obtain the properties that are similar to leased lines. So using some of the DDoS protection systems, you can even get some communication guarantees that approximate having leased lines between all the different entities that are connected. So then the use case essentially that crystallized was that if you have such an ecosystem of entities who all need to communicate and they're not the same company, then it actually makes a lot of sense for them to all get a SCION connection and get the benefits of almost leased line-like connectivity at the cost of a public internet connection. And so the Swiss banking environment realized this, and they then pushed and started trying out SCION, and then pushed the SCION network for communication across the Swiss banks. And for most, the Swiss National Bank and SIX, who are, SIX is the financial provider to many Swiss banks, providing all kinds of applications. They also run the Swiss Stock Exchange. They essentially saw the promise of this technology, and they then worked with the ISPs to establish what they refer to as the SSFN, the Secure Swiss Finance Network, which over several years was being constructed and will be in full use next year when they will turn off the existing finance network. So the decision came last year that they'll actually turn off the finance IPnet, which is today's finance network, and all the banks will communicate over this SCION network. And so this, essentially, this use case then drove the whole infrastructure with the creation of the SCION production network, and this is a real network that we call is also BGP free, because at no point do you rely on BGP to actually being able to communicate. So it's really an independent interdomain routing infrastructure with, you can see a number of entities already who are providing services. And so this was all possible because of this finance use case, and that has driven all these entities to participate. Then a bit over a year ago, then the healthcare industry came along, and they said, well, they were looking for a technology that could also protect communication between doctors' offices, pharmacies, hospitals, and the healthcare providers. So it's again one of these very heterogeneous ecosystems where having leased lines doesn't make sense, because a doctor's office in many cases are just 2-3 people, right? A small office and a doctor, you cannot purchase a leased line to all these different doctor offices. And so they looked at the SCION technology, and because of the maturity of the whole ecosystem, within a year, they were able to connect 50,000 doctors that are now communicating over the SCION network with the medical providers. So this is already now in operation. And what made this feasible was a technology called the gate. The gate essentially is a conversion from regular IP traffic to SCION traffic, which is installed at the ISPs. And the gate essentially attracts traffic to certain destinations by using intra-domain routing announcements. So traffic for a given data center by the healthcare provider is being announced. The prefixes are being announced, and so traffic from the doctor's office goes to this gate device and becomes SCION from that point on. And so it's then delivered as a SCION packet to the destination. So with this technology also, secure home office was being enabled, and so some banks also enabled all their home users to log into the bank over this technology, essentially making the home user and preventing denial of service attacks and making them independent of routing attacks. So this is also in operation today, and now enabling this healthcare industry. Then what happened was, next the energy industry also looked at this, and they said this is also great for energy. They also have similar issues. And many other critical infrastructures are also now looking at this technology, foremost within Switzerland, but also many other countries are also now looking at adopting this technology for protecting critical infrastructures. So thanks to all this, quite a nice ecosystem has formed of also research institutions that make use of SCION, and ISPs offering us. There are many more users here that are not shown. This is because all the Swiss banks are now getting SCION connections. but also it's really nice is a whole ecosystem of consulting firms and security companies that are integrating SCION solutions into their products that then enable the rollout to customers. So this all looks great, but we're still not quite there yet, right? So there's still a lot of work to be done because we still have quite a few of these dependency loops. And let me tell you briefly how we came about trying to handle these different dependency loops. So first of all, one thing we notice is if you go to the number one, to the incumbent company to deploy something, usually the incumbent is not that interested, right? They see one of their own businesses may be impacted by this new technology, and so typically they're not interested. But if you go to number two or number three, the response is oftentimes quite a bit more positive, and they are interested in competing with the incumbent and also increasing their market share. So that has been a great way to actually getting the adoption to speed up. So these are very general things. One point also was the standardization efforts within the IETF that were started to remove these dependencies between standardization, enabling also minimal network upgrades so that to deploy SCION, it's actually quite simple and requires quite little amount of effort to break this cycle. Also requiring minimal changes to the local network equipment, including running on commodity hardware in pure software and using IP-UDP as a local layer 2. So it's really not dependent on BGP, but for local communication, having an IP-UDP encapsulation helps a lot with the rollout. So then there was no need to have network hardware support. And then, of course, also operating system dependencies, etc., through a technology I'm going to present. So essentially enabling a simple application to use SCION directly, even if the operating system doesn't know about SCION, for instance. And then I'll show another system called SBAS, which then also removes the dependency between applications and essentially can put traffic on the SCION network without the sender even sending anything, even knowing about the SCION protocol. So if you look at it, what was needed was ISP deployment, institution deployment, standardization, and all this. And essentially, you can look at it as trying to erase this blue line from all the way at the bottom to getting, for all these things, getting a lot of ISPs to deploy, lots of institutions, standardization, trying to get this blue line up as straight as possible. And the analogy is like a ratchet. So if you're lower, but the line is higher, it becomes much easier to move this one up. But then actually lifting the line takes more effort. So this is just a way to illustrate and provide an analogy about how you can go about trying to resolve all these different circular dependencies. And it indeed is the case when this line is higher, when you made a lot of progress at one point, it is indeed much easier then to increase user demand or enhance application support. Another way to visualize this is through a wheel. So you have, again, the same 6 aspects, and you're trying also to keep this wheel round, right, to really be able to drive smoothly. If you made a lot of progress in one dimension, you should really stop, and because it's important that all these dimensions are roughly in sync, and so that's just another way to demonstrate or to illustrate, I should say, how we went about trying to get more and more adoption for SCION. So now, how does it actually look like if you want to make use of SCION? So at a university, you would have this black infrastructure, and adding SCION, essentially, all it takes is adding a single workstation with the SCION software installed that then connects to either a National Research and Education Network, an NREN, or go through a commercial ISP to some SCION providers. So we're trying to avoid making use of IP overlays, which is kind of what's shown here, because there's no SCION router in that particular commercial ISP at the top left. But that's also a possibility initially to try it out, to install this SCION router and then use an IP overlay. But again, we're trying to limit that, because then you have dependencies on BGP. So within the university, then once you have a SCION router installed, you also need to install a control service. That's this path service I talked about earlier, or also the beacon service that then receives these routing beacons and sends them to the path service and so on. So this can also run on any host or on a virtual machine anywhere in your network. And so once this is configured, one border router and one control service, any host at the university who has IP connectivity to these nodes can now make use of SCION. Right? So there's a bootstrapping system that can just bootstrap directly from the application to find out these IP addresses, essentially, of these services, and off you go. Your application can now send SCION packets. So it's really quite interesting how little is needed, and the bootstrapping service makes use of DNS or DHCP, and to essentially provide the trust root configuration of the local ISD, as well as the IP addresses of the border router and control service. So it's quite straightforward to do this. And then there's different end host stacks. Either you can make use of a native SCION implementation to upgrade an application directly, or you can make use of this translation service I showed earlier to, in that case, the end host is even unaware of SCION, and the packets get translated then on that separate host. But there are several end host stacks out with multipath ability to essentially use SCION natively directly from the application. So what's interesting now is a lot of technology is out there, but again, we'd like to get more applications to support SCION. So how do we do this? So the belief is that if we had about 1 million hosts worldwide who are in networks with SCION connectivity, then the belief is that this would entice application writers to try it out, right? If you have an application that is widely distributed, if you have 1% of, say, users at the university, you may, in this case, you will have 10,000 users globally that then will send you traffic via the SCION network. And so we believe this is a good way to get started. And so the idea is to make use of university deployments and have several national research and education networks and universities who embrace innovation to start getting an access, and then having all users then that essentially are in SCION-enabled networks. So as soon as these users then would have a SCION-enabled application, they could then communicate. So the question, though, is how to convince universities. You need some compelling use cases. It's essentially, one use case definitely is to have a new research infrastructure, having a true next-generation network infrastructure that anyone can use at universities. Any student could just, once it's there, for instance, at ETH, any student can now install a piece of software on their host and just make use of SCION without asking anyone else. It just works. And so this enables a lot of different research projects in security or multipath research and so on. Also for DDoS defense, I'll show an example in a few slides. It turns out universities are starting to be attacked. And there's also this SCION IP gateway that translates from IP to SCION that can be used. I'll show an example of a Brave browser with a SCION extension and then an application we wrote for high-speed file transfer and the firewall, and then I'll also briefly talk about SPAS. So I'll be happy to distribute the slides. There's a lot of different research opportunities with respect to a next-generation internet architecture, so we can take a look at that. And here's DDoS attacks that just happened this year. There was one case especially that SCION could have helped with, where a telescope was attacked for an extended time period. And if this institution would have had a SCION connection, it would have been easy to migrate this telescope's traffic to be able to continue using it. But during the attack, the telescope essentially was unusable. Cases like the University of Michigan, this is harder to protect because here it's a whole university that was attacked. Where, with lots of students from home, from their cell phones and so on, so that this would be much harder to protect, although SCION could have also helped here to enable the administrators, for instance, to log in, to fix things, and for some critical applications, they could have been moved using the SIG technology, for instance, onto the SCION network. So that would have been possible, but this is more a medium-term issue there. So an interesting case we looked at was, what does it take to actually SCION enable a browser? So we worked with the Brave team to build a native SCION connectivity directly into the browser. And here's a demo of Chrome on Mac OS making use of SCION. And actually this web page now, you can click, you see the web page itself was fetched through SCION, but then the Google and the other entities don't use SCION, so that came over the IP network, the standard internet. And this page, for instance, is purely available over the SCION network. And so you can look at the path and so on. So you can, with quite little effort, deploy SCION on a Mac or even Windows computer. And this is still a prototype, I need to warn you. This is not the production. But it works. Once it's installed, it works really well. And without any changes to the operating system. So this is going over the real network. They set up a mirror for this. Of course, BBC is not on the SCION network yet, maybe I can say. And so nothing was downloaded over SCION. So this is something you can start using today. So if you have sensitive data, for instance, for some research purpose, you could, and students need to access this data for some project, and you could actually install this system already today, and SCION enable the web server, again, through a reverse proxy, as you could see with the ETH website, and there's a regular Microsoft web server, and we put a reverse proxy in front of it to then enable native SCION access to that website. And so with this technology, you can now ensure for a research project that your traffic doesn't leave a certain jurisdiction, for instance, and that can be used today. Another application we wrote was Hercules, and another one is Lightning Filter, high-speed file transfer and firewalling. And here's an example running Hercules at ETH. Should start. I need to click. So, oh, okay, now it's starting. Which essentially can achieve quite high speeds for point-to-point communication. This now is within Switzerland, but we showed very high data rates also around the world over the SCION network, thanks to the PCC congestion control system and very efficient implementation. Hercules can actually, even from a single host to another single host, achieve close to 100 gigabits per second, which is quite surprising. That's pretty fast. So, and here is actually Hercules in operation at ETH, going over one path, and but ETH has two SCION links to the ISP. So Hercules can also use both at the same time, and then roughly reach double the speed. So this is quite exciting. So if you have some use case where you're transmitting large amounts of data, you could try SCION for this, and we've had quite a lot of success showing some use cases and getting some really nice speedups. A research project together with Princeton University and University of Virginia, we looked at making use of the SCION backbone network for internet-based communication. So the way this works is essentially there's some servers that announce themselves to this SPAS infrastructure and say that they would like traffic to be optimized that should be sent to them. In this example here, this web server signed up for this, and so at all the POPs, points of presence of SPAS, then this information gets broadcast via BGP. So the BGP protocol, the routing protocol, disseminates this information, so a client who wants to communicate with the server, then this traffic goes to this POP node, and then this node analyzes what's the best way to send this traffic to the destination. So it can use regular internet IP or use a SCION backbone to send this traffic. So in this case, the SCION backbone is used, and at the destination, it's being delivered to the end host. So this is actually similar to this gate service I was mentioning earlier. So SPAS is on the research side. It's a research project, and the gate system is a production-grade system that's already in operation of a similar technology. So you can optimize, say, for CO2 or optimize for latency, for gaming, and so on. There's a lot of different ways what the server can say, what kind of internet properties you would like to achieve. So I'm running out of time, and I see Paolo's getting nervous and is going to ready to tackle me. So unfortunately, I have still quite a few slides. I also wanted to talk about the carbon-aware internet, where you can make use of SCION's transparency property to select different paths that are more that generate less CO2. So through this endpoint path control, and so there's different points we've been looking at carbon intensity forecasting, dissemination of this information within these path segments, and then also analyzing what the impact is. So I'll just quickly click through them to give you a high-level gist, but please look at the paper if you're interested in this area. I can tell you actually the networks don't really use that much more energy to send traffic as compared to idle traffic. So it's unfortunately the good news is you can actually for many paths you can find different paths with that have much lower CO2 production. But the bad news is when you send your traffic somewhere else, and we've shown this here, then other routers still run and they're still using energy, and there's CO2 is still being produced. So we then looked at the virtuous feedback though. So this is, so there's a continuation of emitting CO2, but the good news is that this is a signal to ISP who are producing a lot of CO2. And so having alternate paths that would be selected by entities who want to lower their CO2 then increases traffic at ISPs that are greener, and is reducing traffic at ISPs who are using more, producing more CO2, and then they would lose revenue, and they would also need to switch to increase revenue. So this virtuous feedback, we analyzed it, and we found that this could make actually a really big difference. So here's one of the two papers that just talks about the this carbon-aware green routing. All right, so I think I've already talked about this. So just very briefly, this SCION Research and Education Network is nicely expanding now with first universities connecting to it. And we have now about a dozen institutions across the world, and more now are getting connected, thanks to mainly also KREONet. It's a Korean research network that is providing SCION connectivity in Seattle, Chicago, Amsterdam, Singapore, and Hong Kong, as well as Korea, of course. And several universities get connected via this KREONet ring. And also SCION, who has SCION routers in Frankfurt, Paris, and Geneva. You can now connect to SCION and then select these SCION routers directly and get connectivity this way. So this also has been useful. In Switzerland, we have Switch, the Swiss NREN, who has been deploying SCION for almost 10 years. So this has been very supportive. So if you'd like to know more, please, you can search for this book, and here at KAUST, you can get it for free at Springer. You can just get the PDF right away. And then there's information and also about the production network itself, more information. Thank you.